In this video, we're looking at the definition and the domain of rational functions. The definition of a rational function is specifically a function such that f of x is equal to some polynomial p of x divided by that of another polynomial q of x. Another statement that is absolutely necessary in terms of the definition of a rational function is that q of x will never be equal to 0. So with this notion right here, we are actually talking about the domain of all rational functions. So looking at specific examples, f of x is equal to, say, x squared minus 25 over x minus 5. This particular function, to define the domain, all we have to do is identify that the denominator cannot be equal to 0. So we will let x minus 5, the denominator, equal to 0. We will solve this equation for x equals, and then we will identify that x cannot be those numbers. So the domain of this function f is x cannot be equal to 5. The other way that we could write this is negative infinity all the way to 5, using an open parenthesis to emphasize that 5 cannot be included, union with 5 to positive infinity. Again, this is the interval notation of how we would write it. This is an abbreviated way that we can write the domain of any kind of rational function. So another example for a rational function is, say, x over x squared minus 25. In this case, we're going to follow the same rules. I'm going to change this f instead to a g of x, however, so that we can keep it all on the same page. In this case, I'm going to set the denominator once more equal to 0. I'm going to solve this equation. This is a quadratic. To solve a quadratic, we can either factor it, or in this case, we can use the extract the square root method, where we add the 25 to the other side and then square root. I'm going to go ahead and just use the factoring method because I think it's quick and smooth. Again, those two factors are equal to 0, and then I will set each factor equal to 0, so x equals 5 or x equals negative 5. In this case, again, remember that we're setting the denominator equal to 0, we're solving this equation, and x cannot be those numbers. Otherwise, we have a domain issue in the denominator. So the domain of g in this particular case is x cannot be equal to plus or minus 5. Again, if we were to set this up in terms of an interval notation, we'd go from negative infinity to negative 5, union with negative 5 to 5, and then union with 5 to infinity. For the last example, h of x, we'll look at one last function being x plus 5 divided by x squared plus 25. In this particular example, the denominator that we set equal to 0, you'll notice, will not give us any real numbers. If I go ahead and use the extract the square root method, I'm going to subtract the 25 from both sides, giving me a negative 25 equals to x squared. I will then square root both sides, giving me x is equal to plus or minus the square root of a negative 25, and therefore x will be equal to negative plus or minus the negative will come out of the radical, giving me an I, and the 25 will come out of the radical, giving me 5, so 5i. So x equals to 5i is the values that I can't select. Again, x cannot be those numbers. If they are those numbers, then the original function is undefined. Well, if this is the case, however, if my domain issues are going to end up being imaginary, well, then I don't really have any domain issues to begin with, and I can select all real numbers. This is, again, the definition of your rational function, such that I have a polynomial on the numerator and a polynomial in the denominator. If these aren't necessarily polynomials, it is a form of a rational function, but a rational function is specifically defined such that the polynomials are on top and on bottom, not radicals or logarithmic or any other type of function like that. Those are combinations of rationals with other types of functions. And then those are domain issues, again, always setting the denominator equal to 0, solving for x, and x cannot be those numbers.